Good morning, everybody. Welcome to day 3 of UC GIS week. We've got another great day of programming ahead of us. This morning, we have two back-to-back sessions on urban geographies. In this first hour session, we're going to have three 15-minute presentations. Please leave questions in the chat as they come to mind, and then otherwise we will do our Q&A session at the end of all three presentations. First up, I want to welcome Lemon Dorshero of Johns Hopkins University and Julia Cheeseman of University of Alaska at Fairbanks. Feel free to take it away.
Awesome. We're getting the slides pulled up right now, but thank you for the fantastic introduction. All right, so it's great to meet all of you. We are here today to present our first slideshow, like we just said. I'm Lemon Dorshow. I'm an undergraduate at Johns Hopkins University, and I'm here presenting with Julia, who I'll let her introduce herself.
And I'm Julie Cheeseman. I am a first-year master's student at the University of Alaska Fairbanks.
Thank you so much, Julia. And this work was completed in the summer 2025 term of the NASA-developed national program with both Julia and me, as well as our teammates Anna Valcarcel and Grace Markel. And it's the second part of a greater Florida ecological conservation project. So diving into this project, we're going to start with some background. So first, it's important to talk about the region that we focused on within our study. Southern Florida is home to numerous ecosystems, such as those found in the Biscayne and Everglades National Parks. It's also home to cities such as Miami, and for these reasons, the area is key commercially for industries such as fishing, tourism, and agriculture, as well as ecologically due to its biodiversity and sprawling habitats. Two of the phenomena that we studied pose threats to this region, though. The first is harmful algal blooms, or HABs, which are caused by an overgrowth of cyanobacteria in a body of water and can be either man-made or natural in cause. The second are sediment plumes, which are largely caused in this region by hurricanes or seagrass die-off, and they displace sediment from the seabed.
Thank you, Lemon, for that background information. Jumping into some community concerns, both HABs and sediment plumes can be detrimental to both ecosystem as well as human health. HABs have been shown to increase fish mortality rates as well as decrease water quality. Sediment plumes have also led to some aquatic species die-off and declines in general ecosystem health. These community concerns were brought to us by our project partners that are local to Southern Florida and are a large motivation for the work that we will show you today. And our work hopes to provide information for our project partners to inform their decision making. And I'll pass it back over to Lemon to introduce those project partners.
Thank you so much. So in response to those community concerns, we partnered with two local organizations for this project to provide key insight into the region of Florida and its ecosystems. Our first partner is the Florida Fish and Wildlife Conservation Commission, who's a state agency that utilizes research and technical knowledge to provide resources for environmental management and conservation efforts. Our second partner is the Bonefish and Tarpon Trust, or BTT, and they are a nonprofit organization dedicated to the conservation and stewardship of the bonefish, tarpon, and permit species, habitats, and fisheries. These two partners also assisted us in the first term of the project and are continue to collaborate with us in the second term. And it's worth noting that we also refer to the Florida Fish and Wildlife Conservation Commission as FWC, as well as their associated Fish and Wildlife Research Institute as FWRI. Then moving on to some project objectives. Term one was mainly focused on evaluating different water quality parameters to analyze their impact on the tarpon fish species, seagrass, and mangroves, while we conducted a more targeted analysis in the second term, specifically focusing on HABs and sediment plumes. Our objectives for this project were to observe the occurrences, analyze the impact, and forecast the presence of harmful algal blooms, sediment plumes along the southern coast of Florida using climate data, remote sensing, and statistical methods. And then, yeah, I'll hand it back to Julia for our study area and period.
Awesome. Thank you, Lemon. So here we have our broader study area of Southern Florida, which is outlined in blue. This includes both the Everglades National Park as well as the entirety of the Florida Keys. And this is consistent with the study term that was used in the first term of this project in the spring of 2025. For our term, in term two, we chose to focus specifically on an estuary known as Florida Bay, which is outlined in green here. And this estuary is bordered on the north by the Everglades and on the south by the upper Florida Keys. And we chose this particular area because of the presence of the particular HABs known as Synococcus cyanobacteria, and that was the particular species that we were interested in and was brought to us by our project partners and helped to guide where we focused our work on. And then we also focused on the time period of 2016 to 2025, as that was what our project partners sought to look at for our work. And then if we head to the next slide, we can look at some of the Earth observations that we use for our study. So we use both the Sentinel-2 as well as Sentinel-3, as well as one of NASA's most recent Earth observing satellites known as PACE. And Sentinel-2 was used for both the mapping and time series of spectral indices that we'll introduce throughout this study that we use to study both chlorophyll A as well as water turbidity. And then we also use Sentinel-3 to inform our to inform our HABS forecasting model. And then lastly, due to some missing data gaps, we use the harmonized Landsat and Sentinel data collection from Google Earth Engine to fill some gaps for the 2016 to 2018 period.
Awesome. And moving on to or in combination with the Earth observations we used, we also use several additional data sets that we can go over in this overview of our methods here. And also we can go over the workflow from data acquisition to analysis. So firstly, all of our data was acquired through three platforms. Firstly, NASA's Ocean Biology Data Center, the OBDAC. Second, the Copernicus Climate Data Store. And third, Google Earth Engine. OBDAC provides us with the data from the PACE OCI as well as the Cyanobacteria Assessment Network, or CYAN dataset, which utilizes Sentinel-3. From Copernicus, we obtained the ERA-5 reanalysis climate dataset, which was used as inputs to our statistical model. And then using Google Earth Engine, we were able to access both the Sentinel-2 and harmonized Landsat Sentinel image collections. In order to create our time series and our maps, we merged several datasets as well as applied cloud masking and interpolation using Python before we performed our index calculations. For our forecast, we input the necessary parameters and applied our model fitting in R, and these time series, maps, and forecasts are the end products which we provided to our partners. Then one of the maps we were able to provide is from the new PACE Ocean Color instrument. Having launched last year, the available dataset is still at the provisional level, but it features several products, including chlorophyll A concentrations over the ocean, which can be indicative of HABs. This is an animation of that chlorophyll A product from March 2024 to June 2025. While we applied interpolation and scaling to these visualizations, these maps helped us to understand our study region over the past year in terms of chlorophyll A and harmful algal blooms. We can see the PACE product demonstrates the developing spatial patterns and the seasonality of that chlorophyll A over the South Florida coast, with significant chlorophyll A activity over the Florida Bay area. These spatial patterns we observed help to inform us where we should concentrate most of our analysis, and we focus on the Florida Bay specifically for our index calculations, which Julia will dive into now.
As mentioned previously, we acquired Sentinel-2 through Google Earth Engine, which we used to calculate our two spectral indices. The two indices were the Normalized Difference Turbidity Index, or NDTI, and the Normalized Difference Chlorophyll Index, or NDCI. And using these two indices, we were able to calculate some temporal statistics to look at both time series as well as map visualizations that we will walk through in just a little bit. And it is of note that there was some missing data from 2016 to 2018, and so we had to merge the harmonized Landsat data set with the Sentinel-2 in order to fill that gap, specifically for NDTI. And then for NDCI, we were able to look at the CYAN data set for this time frame because there weren't the correct bands in the harmonized Landsat for us to use that data collection. And then if we head to the next slide, we can look at our study period of 2019 to 2024, looking at NDCI in Florida Bay. And as you can see on the screen here, high chlorophyll is indicated by the green colors, whereas low chlorophyll is indicated by the blue colors. And as you can see, the chlorophyll follows a west to east gradient with higher concentrations of chlorophyll in the west part of the bay and lower in the east. And this actually aligns with some really notable freshwater flows in that northwestern part of the bay. As you can also see, in 2024, there's the largest extent of that green area, so highest chlorophyll presence. And if we compare those with our turbidity findings for the same period and same time frame, On this map here, higher turbidity is indicated by the darker color and lower turbidity by the lighter colors. And we actually found that all of our turbidity values were below zero, which is consistent with a previous study done and also in a marine ecosystem on the western coast of Florida. And as you can see, turbidity follows a very similar pattern to chlorophyll being highest in that west part of the bay and lowest in the east part of the bay. Turbidity is also highest around the coastline as well as the interconnected basins within the estuary, which aligns with a lot of sediment mixing that occurs at that area. And we can look at the same data for both NDTI and NDCI on the same graph. And to orient you to this graph a little bit better, NDCI is located on the left axis and indicated by the blue line, and NDTI is located on that right axis indicated by the orange line. As you can see, both indices vary seasonally as well as yearly. They follow very similar seasonal trends, rising in the spring and peaking in the summer months, and then falling in the winter and fall months. Several storm events are indicated by the vertical dash lines on this graph, which show its impact on both these indices. We found that turbidity and chlorophyll were highest in the summer due to the occurrence of more storms, which leads to more sediment loading, as well as just influx of fresh water coming down from the Florida Everglades into Florida Bay. And then the last thing of note is that the chlorophyll reached its peak in 2024, which is consistent with the general increase in persistence of the Synechococcus bacteria in Florida Bay, as was noted by our project partners through on-the-ground observations. And I will pass it over to Lemon to talk about our forecasting model.
Thank you so much, Julia. So in addition to our time series and maps, we also wanted to inform our partners' management and conservation efforts through the use of forecasting models for cyanobacteria concentrations within our study area. To this extent, we use both an autoregressive integrated moving average, or a REMA model, as well as an ARIMA model with exogenous variables, known as a REMAX. The ARIMA model only considered the cyan datasets records of cyanobacteria concentrations, which were given by a cyanobacteria index that is proportional to concentration, while our REMAX model was able to factor in sea surface temperatures and precipitation as well, which were selected out of a greater list also including surface pressure, air temperature, and sea depth due to their statistical significance. From here, we were able to produce monthly forecasts for cyanobacteria within our study area, which can then be assessed and refit as future cyan data becomes available. And on the next slide, we can go over the first set of results we have from these forecasts. So visible on this chart is a comparison of our model's accuracy, in which both models are used to calculate expected values at each month during the fitting process. Both models achieved under 10% mean absolute percentage error, or MAPE, which by our benchmarks is incredibly accurate, though a Remax did end up reaching higher accuracy by about 1%, likely due to its use of those environmental factors. We're still very happy with the accuracy that both models achieved. And on the next slides, we can go into some of their forecasts. So given the accuracy that we just discussed, we were then able to forecast cyanobacteria concentrations through the end of 2025 with 90% confidence intervals represented by those bars on the plots. ARIMA's forecast is a little bit less exciting, predicting a constant value through the end of 2025, while the REMAX's forecast shows more variation due to its consideration of environmental factors in its calculations. However, we do expect both of these forecasts to reasonably encompass cyanobacteria concentrations through the end of 2025, with of course special focus brought to that first month forecast, as it's likely the most accurate. Then on the next slide, we can talk about some of the errors and uncertainties we faced throughout our project. The forecasting statistics we just reviewed wrap up the results themselves, but as with any study, there are multiple errors and uncertainties that we wanted to consider. To start, our study region covered a substantial portion of southern Florida, which meant that averaging over this large study area, even when we narrowed down to the bay, could sometimes cause skewing of some values. In our data acquisition, we also found that there was missing Sentinel-2 data, and only specific collections were available to us through Google Earth Engine. To fill in any data gaps in our processing, we merged some data sets, employed interpolation, and applied cloud masking to our satellite images, all processes that of course introduce inevitable spots where error may pop up. And then finally, cyan data has typically been used in freshwater ecosystems, but we did apply this data to a saltwater ecosystem in order to fit our forecasting models. Altogether, while there are some limitations in our findings, we accomplished our project objectives and found our methods to be feasible, which Julia will elaborate more on now.
So develop is special because we only have about 10 weeks to complete this project. And so within those 10 weeks, we're able to study both spatial and temporal trends of both sediment plumes and HABs in Florida Bay using several NASA and ESA satellites in conjunction with some extra data sets such as cyan. We were also able to use PACE OCI, which is one of NASA's newer Earth observing satellites. And even with the provisional level and coarse resolution that you saw in this presentation, we were still able to observe some pretty key spatial trends and seasonality of chlorophyll A activity, specifically in that southern Florida area. And then lastly, using the historical data, we were able to develop the forecasting model that Lemon just walked us through to predict the occurrence of future HABs through the rest of 2025. And after the slide deck was completed, we were able to create a more advanced spatial temporal model that is not included in the slide deck, but is included in our technical paper. And so if you're interested in reading more about that, I direct you to our online technical paper. And then if we wrap together with some partner implementation, the forecasting models that we created help to inform coastal management and conservation efforts in the Florida Bay area. And then the maps and time series we created help our project partners to understand the location, extent, and also impact of these sediment plumes in our Florida Bay area. And then I will pass it off to Lemon to wrap up our presentation.
So as we wrap up, there are a few key takeaways worth noting. Both sediment plumes and HABs had similar seasonal patterns and responses to severe weather events, highlighting their interconnected relationship. Additionally, we found that Earth observations, including the novel PACE satellite, can be used to observe the spatiotemporal trends and seasonality of water quality parameters like chlorophyll A in South Florida, even with the current provisional level data. Finally, both ARIMA and ARIMAX forecasting models, as well as advanced spatiotemporal modeling, can serve as valuable HAB projection tools when coupled with remote sensing and weather data. I'd like to reiterate what Julia mentioned about the more advanced spatiotemporal model that we were able to complete after the slide deck was completed. Of course, while the results are not in this slideshow, they are available in our technical report of the same title as this presentation on NASA's technical report server. Then finally, on the next slide, we'd like to go over some of our acknowledgments for the project. Once again, we'd like to thank our teammates Anna and Grace for the work they contributed to the project during the summer term. We'd also like to thank our project partners from FWC and BTT, Matt Garrett and Aaron Adams, for their valuable local insight and knowledge. Additionally, we'd like to thank our science advisor, Dr. Gilmore, as well as our Develop Center lead, Katie Miller, and Impact Analysis Fellow, Maya Hall. And finally, we'd like to thank the Term 1 team for all of their valuable findings and past contributions to the project. Thank you, guys.
Thank you so much, Lemon and Julia. That was excellent. And a reminder, please put any questions you have in the chat, and we'll also do our Q&A at the end. And oh, thank you to Katie, who has posted in the chat a link to that technical report mentioned by our presenters. Next up, I want to welcome Kyle Emery of UC Santa Barbara to talk about dune restoration.
Thanks. Let me just see if I can share the right screen real quick. Okay, can you see that?
Yes.
Okay, perfect. Great. So thanks for having me today. My name is Kyle Emery. I'm a research biologist at UC Santa Barbara in the Marine Science Institute. And today I'm going to talk about some of our coastal resilience research and how we've integrated some GIS methods into this work. Specifically looking at coastal resilience on an urban beach. So the justification for this work that we've been doing is thinking about coastal vulnerability and how different ecosystems, communities, and infrastructures are facing rising threats from sea level rise, disturbance events like El Nino and winter storms, and the combination of sea level rise and flooding scenarios on top of storm situations. So these impacts are projected to increase over time. This is a projection of coastal inundation from the Cosmos coastal storm model under sea level rise scenarios. So it demonstrates really that there's quite a bit of potential flooding along the coastal zone with the added impacts of sea level rise. However, there are a number of approaches to respond to this coastal vulnerability from both sea level rise and storm threats. The focus of these coastal adaptation approaches is really on a gradient from prioritizing natural features to more hybrid or structural features. What I'm going to focus on is the results of a pilot research project testing how we can restore natural features in an urban setting and not be reliant on hard infrastructure like seawalls or rock revetments. So in this case, I'll be talking about dune restoration. Um, and thinking about dune restoration in an urban setting, why do we want to bring dunes to beaches that might already be particularly wide beaches or have a lot of sand? Really, it's to restore these ecosystem services on top of the coastal resilience benefits. So dunes buffer sea level rise and storm erosion. They promote sand accretion and retention. They're important for recreation, education, and cultural benefits. They support biodiversity, including a number of rare species, and also ecological functions like nutrient cycling and carbon sequestration. So today I'll talk through two different research efforts centered on the Santa Monica Beach pilot dune restoration project, including how we've integrated some remote sensing through drones and GIS into these analyses. So like I said, the idea of nature-based shoreline protection was the goal here. There are a number of benefits achieved through sand accumulation and vegetation establishment and the co-benefits between those two. So here we had an ability to test out a unique restoration design with community input and test how we can use a cost-effective approach with multiple resilience and ecological benefits to better buffer this beach. So just for some background on the study site, Santa Monica Beach is in a heavily urban setting in Los Angeles that has high recreation use. The beach has been groomed intensively for more than 70 years on a daily basis. So beach grooming is just the raking of the beach by tractors to clear any sort of debris, but it also eliminates kelp rack inputs, dune vegetation, and really just flattens the site or flattens the beach on a daily basis. There's plenty of sand on this beach. It's had a long history of nourishment. And the idea is to test out a cost-effective approach to restore dunes using a very small pilot study area of 3 acres. So this was conducted with kind of minimal manipulative efforts, fencing, broadcast seeding with native dune plants in December of 2016, and then just tracking and evaluating the natural establishment of dunes within the fenced area. What we did was we did a bunch of on-the-ground surveys over time, looking at vegetation establishment, elevation surveys using a drone where we use the orthomosaic imagery that's produced and the elevation models, and then a number of other biological surveys at the site, which I won't go into today. So just to show some before and after images of the site, December 2016 when the project started on the left and January 2023 on the right. So this shows the development of that foredune across the front of the site and vegetation establishment. Along the perimeter sand fencing that went up, initially you could see some dune formation beginning after the first year, and then 5 years later, the full establishment and actually burial of that fence by the dunes that have formed. And then this view looking across the site, again, you can see vegetation is largely established across the entire zone, and then the fencing has promoted that kind of perimeter dune. And this is important because the site is being naturally engineered by these native dune plants. So it's really important that we're using native species here and controlling for invasive species at the same time. So we conducted a full evaluation of the project 6 years after restoration. The reference for this project is on the right of the screen here. And this overhead view from the drone just gives a really good example of how that project really is just an island in the middle of this groomed beach. But you can see the dunes that formed around the perimeter where the fence is, But importantly, what I want to draw attention to is what's labeled as that incipient foredune, the dune ridge that's formed kind of parallel to the waterline. That's really important because that foredune formed naturally without sand fencing in that location. So that's where sand and vegetation would naturally settle and develop at this site based on the wave and wind climate. So through our analyses here, we were able to look at sand volume change over time. So this is the accumulation of sand in the restoration versus the controlled site. So the restoration site did level off over time, but it was definitely greater sand accumulation than what was observed in the control site. And using the results from our drone analysis, we were able to develop a digital elevation model of the site. And what this allows us to do is not only to model the accumulation of sand across the entire site, it also allows us to estimate the volumetric addition of sand to the site. So across the entire site, volume 2,700 metric tons of sand, or 19 metric tons per meter of shoreline, accumulated within the site, and 32% of the added sand was in that highlighted foredune ridge that you can see across the front here. And the reason that I'm again mentioning the foredune ridge is that's where we're going to focus on for thinking about the actual protective abilities of the site. And again, just to show that vegetation response across the time series, we had a very large increase in vegetation cover, and that compares or contrasts well with that groomed control site, which remained at 0% vegetation for the entire study period. We were also able to identify natural zonation processes in the plant distribution across the site. So here I'll just draw your attention to the middle panel here, where we can see that different plant species dominate at different locations across the site. And the areas where we have the greatest plant cover correspond to the areas where we have the greatest sand accumulation across the site. And this is just interesting because the seeding was done uniformly, and then the plants naturally zonated over time. So we're also able to evaluate these vegetation dynamics with our drone imagery. So using our two different drone sensors, we were able to produce color orthomosaics of the site and multispectral NDVI-based mosaics of the site. And then in using a random forest classifier in ArcGIS, our goal here was to determine vegetation cover across the two different methods. And we actually found really strong agreement in total vegetation cover between the color and the NDVI imagery. And this was also within the margin of error of our estimates of vegetation cover on the ground. So it was highly agreeable between all three approaches. What we're working on next, using some kind of AI and deep learning approaches, is to attempt to also distinguish the dune plant species in these orthomosaic images. But getting back to our kind of original question is, how does this actually increase resilience on the beach? So we know that we can develop these natural dune systems. They accrete sand, vegetation grows, and they appear to develop into these natural large dune systems. But how can we actually test whether or not that confers any resilience to the site? So in thinking about this restoration performance and functional resilience, we had the opportunity to evaluate the actual dune resilience against a large wave event. So December 31st, 2023, there was a large storm in California, which was in terms of the wave height, Santa Monica Bay saw roughly 3-meter waves that day, which puts that particular day in the top 15 of wave days in the past 23 years. So it was a very large wave event that would provide us a great opportunity to look at the impacts on the dune site. So this picture on the screen now is the Dune site during a summer survey. And now we can look at the site after that storm event. So what I'm highlighting on this overhead shot from the drone here is the restoration area and then our control area to the north. And that black arrows are pointing at the total water level, which is the wave run-up distance on the beach. So you can see within the restoration site, that total water level line is right along that Fore Dune Ridge. But to the top of the photo, outside of the site in the control, you can see a much further incursion of that wave run-up on the beach. So again, this project, the citation is on the right side of the screen here. And what I'll talk about next is how we took our drone imagery from this site and actually evaluated the differences between the control and restoration site. So this figure on the left is the drone orthomosaic from that day with the total water level line delineated in yellow across the entire scene. So you can kind of visually see just looking at the restoration site where that water level line follows the Fore Dune Ridge toe. But then outside of the site, you can see a much farther back incursion of that water line onto the beach, even interacting with some of the infrastructure, such as the beach boardwalk. Above here is the normalized run-up distance from these different locations, the north side of the restoration, the south side of the restoration, and the control. And again, you can see the run-up distance is much higher up in the control site and also much more variable compared to the restoration. On average, across the entire site, there was roughly 14 meters or 50 feet greater water incursion at the control site compared to the restoration. And one way to think about this is how is that water incursion or that run-up distance controlled by elevation differences inside and outside of the study site. So the run-up elevation height-wise was actually comparable inside and outside of the restoration site, which makes sense. It was just found at a much more seaward location in the restoration area because of those higher elevations and steeper beach face produced by that Fore Dune Ridge. So this image on the bottom here is our elevation elevation model of the site, where you can see that Fore Dune Ridge across the front of the site is exactly where that water run-up stopped. And then outside of the site, you can see a much flatter beach face, but similar elevations to where that water run-up line is. And on the top here, you can just kind of see these average elevation profiles across the site for all three areas, and where we see that that run-up distance occurring for the restoration sites and then further up the beach for the control. So just to summarize here, we've demonstrated that this is a long process to utilize nature-based restoration, but it works. We can get sand accretion, vegetation, and natural foredunes developing within several years from project implementation. There's large vegetation dynamics and gains across the site, but importantly, we're also seeing large elevation gains across that Fore Dune Ridge. And the reason I call that out again is that we're seeing, 3/4 to a meter of sand increase along this Fore Dune Ridge in a time period of roughly 5 years. So in terms of thinking about sea level rise and the rates of sea level rise, these dune restoration projects, this one as a prime example, demonstrate that we can produce positive elevation changes at much higher rates than current sea level rise rates. So just that demonstrates the true effectiveness of this over time. And like I said, that Fore Dune Ridge, which is the primary defense mechanism, our elevation model analysis showed roughly 3/4 of a meter to a meter gain in elevation there. But importantly, the entire site still, on average, gained roughly 20 centimeters in elevation across that time period, even in the middle of the site, which is much less likely to interact with waves and storm situations. But it shows that in general, the entire site has demonstrated accretion over that time period. And that just indicates really the longer term resilience benefits that can be produced by these restoration efforts. So as I said, we're working now to incorporate some further GIS analyses to distinguish the dune plant species across the site, and then just develop longer term time series of these elevation models where we can really evaluate the resilience and benefits of these dune restorations over time and against different disturbance events. So with that, I'd like to thank you, and my email address is listed here if there are any questions. And I can also provide the references to the two papers about this project if anybody's interested. Thanks.
Thank you so much, Kyle. I know I definitely have questions for you at the end of this session.
Yeah, of
Uh,
course.
let's see. Next up, we have our third and final presentation before we get to our Q&A. We have Samuel Sharp of UC San Diego to talk about SB 79.
Hello. Go ahead and share my screen. Hello. So this morning I want to talk about SB 79, which is a new housing policy here in the state of California. But more broadly, I want to talk about some of the issues in dealing with government data, especially with public transportation, and some things I think we should do to kind of improve the usability of government data, especially with regard to housing and transit. First of all, quick introduction. Hi, I'm Samuel Sharp. I'm a first-year undergraduate student here at UC San Diego. Big fan of trains and transit and sustainable housing policy. And I'm here kind of semi on behalf of one of my organizations, Build SD, which is kind of a community organization that documents projects that are being built around the city. So we have data from city permits as well as our own editorial coverage. And we just kind of try and paint a picture of what's being built. And one of our major projects recently has been analyzing Senate Bill 79, which is Scott Wiener's bill that overrides local zoning in major urban transit counties across the state and allows denser infill housing near a lot of major transit stops. So not local bus, but bus rapid transit and major rail. However, there are a lot of parcels that are going to be delayed from their SB 79 upzoning until the next RHNA, Regional Housing Needs Allocation cycle in 2031. And this can be due to high fire risk, low opportunity zones, the maximum density already allowed, historic zones, or any combination of those factors, how upzoned it already is. And some sites are outright exempt. And so in trying to kind of create a visualization and a map of SB 79 enabled upzoning across the San Diego region, we've run up against a lot of these challenges in the data we have to deal with. And so we've identified kind of three core problems in working with this data and putting together this analysis that I want to kind of share with you this morning and talk about how we're dealing with. First of all, government open data can be annoyingly inconsistent, especially with regards to GTFS, which is public transportation data, and zoning data. So GTFS is the open standard for public transportation data. It is an international standard. It was developed here in the US by TriMet in Portland and some other agencies. And now almost every transit agency in the US is required to release and report GTFS. However, that data can be of varying accuracy and oftentimes doesn't line up with the data of other agencies or with state policy guidelines. So for instance, SB 79 sets strict limits on what is heavy rail, light rail, commuter rail, high frequency commuter rail, and oftentimes the GTFS data doesn't line up with that. For example, in the top left, it's not a California example, but it's the most jarring one I can find. This is DFW Airport North Station outside of Dallas. Both of these train lines use the same technology. They literally run on the same tracks. But Trinity Metro marks Tex Rail as light rail, whereas DART marks the Silver Line as heavy rail, specifically heavy commuter rail. Are either of these designations wrong? I don't know. I don't know what the legal definition is in Texas, but this is how each of those agencies wants to represent that to their consumers. And because GTFS is such a consumer first, kind of consumer forward technology and it was originally created for inclusion in Google Maps, there's a lot of times inaccuracies like this can appear when you're dealing with analysis using GTFS data. There's also the issue of what is a station, what is a stop, what is an entrance. In GTFS terminology, a station is kind of a parent location, while a stop is a specific place you can board. So while the SB 79 bill kind of interchanges stations and stops and definitions for kind of entrances in particular. Oftentimes they'll say the entrance to a major transit stop. And that can be annoyingly inconsistent. LA Metro, for example, actually does mark the entrances. You can see in the bottom right, I have a picture of that. A C station actually marks where the entrance is for the station. If we were doing LA Metro analysis, we'd be playing that part of SB79 on easy mode. We would just be able to draw our circles around either the boarding locations or the entrances. But in San Diego, we don't necessarily have that because a lot of the trolley stations are more open. Is it wrong that MTS doesn't provide entrances in their GTFS? No, I'd argue it's not really necessary for the trolley. But does it help us when we're trying to do kind of a consistent standardized analysis that could be replicated in other metropolitan areas? No, it absolutely doesn't. And another issue comes when you try and factor in local zoning. So these inconsistencies compound across municipalities and transit agencies. When you have a complex transit system like the San Diego Trolley, you're passing through a ton of different municipalities. The Orange Line alone, you have San Diego, Lemon Grove, La Mesa, El Cajon, just on a single rapid transit line. And so you need to be able to put together the local zoning from all of those different areas across the state. What we're currently doing just flat out would not be possible at the state level with anywhere near our current team and staff. We have a 3-person data and GIS team. And we would not be able to gather and kind of standardize all of the transit data and all of the housing data and be able to put that together at a statewide scale. And for some cities, zoning just was not available in any GIS format, especially for historic districts. There are a lot of cities where we've had to flat out manually draw the historic districts because there's no GIS compatible data set for that. Big problem number 2, standardized definitions in the legislation itself can be hard to deal with because they're built for policymakers. These are bills that have gone through cycles and cycles of revisions. Each one, neighborhood groups have requested more and more concessions from the bill. SB 79 was weakened a lot during the legislative process. And so each one of those kind of cutouts and carve-outs raises more questions for us as analysts. What counts as a major transit stop, for example? Is it high frequency? The California Public Resources Code lays out a 20-minute standard for high frequency, but almost no city actually uses 20 minutes as their baseline for high frequency. It's usually 15 or 10. If it's based on bus lanes or a dedicated bus right-of-way, what is a bus lane? Does a station bus loop? One of the most recent issues we had to deal with was, does a station bus loop? Like at Rancho Bernardo, Del Lago, Escondido in North County, San Diego, if you're familiar with those. Those are dedicated bus loops into a station. Do those count as bus lanes? Does it require additional BRT scorecard amenities, things like all-door boarding or off-board fare payment? And which, zonings, fire risk ratings actually can delay that upzoning? So here's some examples of like inconsistencies that we actually went and found. The bill calls out commuter rail as a public transit rail service not meeting the standards for heavy rail or light rail. And then in its light rail definition, it explicitly excludes airport people movers. Does that mean airport people movers are commuter rail? No, I think not. I don't think that would hold up in court. But because they have GTFS, and oftentimes in their GTFS they're marked as light rail, that could be something you'd have to deal with in an analysis in another metro area where we actually had an airport people mover. I wish we had one here. Additionally, the development of the key definition of transit-oriented development stop, a major transit stop as defined by the Public Resources Code. And then the Public Resources Code, an existing rail or bus rapid transit station. Well, rail station's easy. What's a bus rapid transit station? Does something like Rapid 215 or 225 count here? I'd say Rapid 225 absolutely has bus rapid transit amenities, but it doesn't have the high frequency guideline. The intersection of 2 or more major bus routes. What's a major bus route? If you go by the MTS definition of, they put a little asterisk next to routes that are supposed to have high frequency. Sure, but again, that's not the state's definition of frequency. And there's inconsistencies even with that. The 936 is a star high frequency route, but it doesn't run every 15 minutes. It runs every 30. I presume it's starred because it interlines heavily with a route that also runs every 30. And big problem number 3. This is everyone's problem now. Agencies and planning organizations are seemingly scrambling to figure out legislation at the same rate we are. SB 79 was an intensely controversial bill. It's now an intensely controversial law, and there will be fights over however we implement it. And there are still a lot of questions we're unsure about. We have solid operational definitions that's been allowing us to do our analysis, and I promise you'll see a couple of maps in the next few slides. But there are certainly still things we're unsure about. And eventually, it's just going to be up to the transit agencies and the planning organizations to work together and kind of evaluate the law's impacts on their communities. And while we'd love to be able to be the first to tell that story, and we're working on it, at the end of the day, we can't be the only ones to tell the story of what it's going to look like in 5, 10, 15, 20 years in this neighborhood. So here's I should have promised maps earlier. I should have had maps earlier, but here's kind of a sample of what we've done with our analysis. So we have our quarter and half mile buffers around stations. SB 79 also requires that we take into account what is walkable within 1 mile around stations. So that's why you see cutouts when there's things like freeways, and why there's those gaps in the buffer. Those are the mile walkability zones, I believe. As well as what areas are delayed or canceled we have in orange or yellow. And so it's been a challenge kind of trying to take so many discordant data sets and run the analysis in a way that makes it clear and simple. It'd be easy if we could just plop down every city's data set, because most of them do have some form of GIS, and we said, well, this is high fire risk, this is low opportunity, and it has all of these zoning codes in the station area. That would be something we could pretty easily do for a large portion of the San Diego area cities. Does that help us if we're trying to tell the story? Does that help us if we're trying to help people visualize, well, is this plot going to get upzoned or not? And I would argue no. To help people kind of understand the story of what would happen in 5, 10, 20 years, we need to be able to show them something where we've already taken into account all the complex legal principles. And we've tried to do that to the best of our ability here, and we have to keep working on it. Originally, I submitted this talk with the title "How Build SD Broke Down SB 79," and then I had to change it while I was building the slide deck to "How Build SD is Breaking Down SB 79." And so government open data is for all of us. And I know I've been using the word story a lot throughout the presentation, but now it's time that we more broadly put that government open data to work in our projects and use it to actually tell stories to people. So with that in mind, I have a couple key suggestions. First of all, we should fund and strengthen projects like the Sanjus Regional Data Warehouse. This is an incredible resource. It provides data on things like zoning across the entire San Diego region. The issue is it doesn't provide all of the data it should be providing, and oftentimes it's in wildly inconsistent formats. For example, it only has base San Diego zoning and unincorporated area zoning because it's a joint powers authority or a partnership between the city and the county. So it has San Diego City zoning and San Diego County zoning, but it doesn't have necessarily zoning for the other cities in San Diego County. And we should make projects like Sanjus more regional and more regional partnerships, so that they can provide that data for all the municipalities they cover. We should standardize transit mode, schedule, and what counts as a major route statewide. We should tackle questions like, is it BRT if it doesn't necessarily run the headways of a BRT line? Can a route be rapid if it's just really fast, even if it doesn't necessarily have amenities like off-board fare payment or all-door boarding? And we should ensure more compliance with GTFS best practices by local agencies across the state of California. Additionally, we should standardize the format for zoning codes and other pieces of municipal data so we can release maybe not a single statewide data set, but so that the local data sets can be available in roughly the same formats and use roughly equivalent codes while still allowing for the nuance of local community zoning. That's all I have to share this morning. Thank you for joining. If you want to learn more about the work we're doing at BuildSD, we'll have more on the map soon there. You can visit us, buildsd.org. If you want to get in touch with me about the project, you can email my UC San Diego email, sbsharp@ucsd.edu. And if you would rather ask me questions on social media, I have that there as well. Thank you.
Excellent. Thank you so much. I think we should give a big round of applause to all of our excellent presenters in this morning's session. I'm now going to open the floor for Q&A. We have about 10 minutes. I haven't seen any in the chat yet, but does anyone have a hand? I know I have a question for our first pair of presenters. I know Florida has a particularly unique ecosystem and habitat compared to most of the United States, particularly the South Florida area that you've been working on. But do you think that the work that you've done, this is something that could be potentially applied more broadly to other areas of the United States or for other like similar but not quite the same issues around coastal areas?
I'd be happy to kind of tackle part of that question. And if Julie has anything else to add, she can. Something really interesting about that question is that, we mentioned in one of our limitations that cyan, the data set, is actually compiled by NASA, NOAA, the USGS, and the EPA, if I remember correctly. And this is a data set that is typically used in freshwater ecosystems in previous literature, but we used it in a saltwater ecosystem. And in terms of the forecasting approach, especially the more advanced model we mentioned we used after the slide decks were completed, that is a model that can be used for cyanobacteria forecasting in like lakes across the US. So we took a lot of inspiration and a lot of guidance from a paper published by Dr. Blake Schaefer at the EPA in 2024, where he looked at freshwater lakes across the continental or the contiguous United States. And in that paper, there was definitely the use of that Sentinel-2 cyan data set, along with statistical methods to do forecasting. So at least on the forecasting half of the project, while we didn't see the use of ARIMA or REMAX, specifically, there's definitely a niche for that Sentinel-2 data to be used for, chlorophyll A or cyanobacteria analysis and forecasting.
I'll also add that the PACE satellite that we use is pretty new. I believe it was launched in March of this year. And so as that kind of gets a few years under its belt, I think that data will be more accessible and be used to scale our work to other coastal areas across the US and potentially the globe.
Fantastic. Thanks so much for sharing. John's got a question for Kyle in the chat, and then we'll go to Sarah's question, asking, do you think Santa Monica and Venice would agree to allowing a foredune?
Yeah, that's a great question. Santa Monica is an independent city within LA County, so their 3 miles of coastline is managed by the city of Santa Monica, whereas the rest is managed by LA County beaches and harbors. Santa Monica allowed the pilot project that I presented about, a second one of a similar size, and now this, probably next month, they're getting ready to start their phase 3 restoration approach, which is actually going to be a 40-acre restoration. It's a little bit unique because it's kind of a patchwork style, so they'll be implementing a bunch of restorations kind of along the coastline. So it will have like gaps in it, but it's a major improvement and increase or scaling up of what's been happening. So it'll be a really great test project for it. Other locations like Venice, Manhattan Beach, Dockweiler Beach, there are a bunch of kind of these pilot size restoration projects that are like 5 acres or less. So it's a good question. I think it's a slow process because there's such an ingrained way of managing beaches there that it's hard to change habits. But there is definitely like noteworthy positive directions in all of these locations, and Santa Monica especially is taking the lead on that.
Thanks so much for sharing. I see Sarah has a hand. Would you like to ask your question?
Yes, it's also for Kyle. Can you talk a little bit more about, you mentioned that you seeded your test area. I would love to know how exactly did you use the seed mix? How did you choose which plants? If you could talk more about that, would be great. Super interesting.
Yeah, thank you. So it was a seeds were collected from LA area existing dune vegetation. So native plants were prioritized, especially native plants that are the dominant ones in Southern California. So the four species that were seeded were just the four most common dune plants that you find in four dunes in Southern California. It was hand collection of seeds from existing plants, and then it was actually broadcast seeding. So that's really just taking the mixed bags of seeds and scattering them kind of uniformly across the whole site and trying the best to time it with the rain season. So doing it in late summer, scattering the seeds like late summer, early fall, and then allowing just natural irrigation from the rain. Other sites install like temporary irrigation just to get like plants started. And you can also use like container stock from greenhouse supply or start them in a greenhouse. But we found that the broadcast seeding actually works really well.
You, Kyle. Lemon.
Yeah, I actually had a question for Samuel. I found that presentation really interesting, especially as another, public transit enthusiast. So I know very different cities because I currently live in Baltimore, which, is also a city with a very extensive history relating to transit and zoning and all sorts of things kind of relevant to the sector. You mentioned a lot of things about San Diego and kind of statewide initiatives, and maybe not knowing, not generalizing too much, I guess. But like, is there any way that you think potentially other cities or other states may be able to implement strategies similar to what you discussed in your presentation, in service of their own transit agencies?
Yeah, so I mean, Maryland is interesting in that I believe it has a statewide agency. I believe the Maryland MTA is okay, yeah, it's a statewide operator. So that means they should be operating under a single GTFS feed, which would actually make it easier to do a lot of the things I talked about here, because their definitions for things like is this light rail, is this heavy rail, are more standardized. And also in Baltimore, there's a pretty clear distinction. The Metro subway link is heavy rail, light rail link is light rail. Purple line is whatever the purple line is. It'll be done in 2045 or something. Um, so yeah, definitely. I think a lot of it's applicable. As for zoning, that depends more on the local municipalities. There, I mostly stuck to San Diego area because those are the cities I know. But I definitely think the idea of kind of a more consistent data format for zoning rules could go anywhere. And I think you're going to have an easier time at it with transit data. What I would recommend looking for is seeing if the MTA has a GIS portal. A lot of times agencies will convert their GTFS data to shapefiles. In our case, for our analysis, we converted it ourselves because we already used raw GTFS for other build SD stuff. So we converted ourselves, but in a lot of regions, they will publish their GTFS stops and routes, not necessarily schedules, but the shapes and lines themselves as a separate like shapefile or another kind of GIS compatible data set.
Awesome. Thank you so much.
And I have a question for you as well, Samuel. What you talked about in terms of inconsistencies among data reporting is something that I've seen as sort of a common theme among several presentations this week for municipal open data and different agencies around the state, of course, mostly California, based on what we've been talking about. I guess I'm sort of asking you to speculate a little bit. Are there ways that folks are perhaps like lobbying for improved standardization of data reporting or things like that that we might be able to do as a researcher community here of UCGIS folks to try and get better, more standardized data from all of these gazillion state, municipal, city agencies out there?
Yeah, so I don't know of any particular project right now that's focused on data cooperation. I do know if you're talking about public transit data, there is a project called Cal ITP that is intending to kind of integrate the state's transit systems more. It seems like they've been focusing a lot on kind of fare and payment integration, which I like my Pronto cards. I'll stay out of that. But um, They are focusing on how to integrate statewide transit systems more closely, and so I think they would probably be a good starting point for creating some kind of statewide GTFS reference. And I believe that's something they have kind of dipped their toes into. From a more general perspective, I think kind of being able to hold up some things that have worked, like SanGIS here in San Diego, which is a partnership between the city and county and our MPO, Sandag, kind of being able to hold that up and say, well, it's not perfect, but this is what happens when you at least try to create a regional data warehouse, a regional data set. So I'm not familiar with any group that's doing that integration work right now, but there's definitely starting points that I see for it.
Awesome. Thanks so much. And thank you again to everybody. One more big round of applause to these three excellent presentations. Please join us for our next session starting right about now on Urban Geographies #2. We have another three great presentations at a separate Zoom link. Please go to our calendar for that link, and we hope to see you all there.
And it's the UC San Diego Zoom link too, I believe.
Yes, it is. All right. Thank you.
Thank you all.